Welcome to part 2 of energy cost of physical activity. So let's talk about some of the commonalities. When we're calculating energy expenditure for walking, running, cycling, there are going to be some things that we're going to do for all examples and all types. So here are three examples, 3 activities. We have walking, the horizontal component of walking and the vertical component. So when we calculate the oxygen cost, which allows us to calculate caloric expenditure, there is a horizontal part. So if I'm walking, there is a flat component and then there is a vertical component. And these are the factors that we'll be multiplying these by speed. And again, I'll show you some examples of that. And then also we're going to be adding rest. So rest is 1 MET, which is 3.5 mils per kg per minute. Again, I'm going to show you an example of that. So notice the horizontal component or the flat component, I have a 0.1 mils per kg per minute, and then it's divided by meters per minute. So my speed dictates my O2 cost. For the vertical component for walking, it's 1.8 mils per kg per minute, and then it's per meter per minute. So again, this is the speed component. So we'll be converting miles per hour into meters per minute for all of these. That's a commonality. Jogging and running, notice it's a horizontal and a vertical component along with rest. It's in meters per minute, so speed is going to dictate the overall cost. With bench stepping, we have the horizontal or vertical. Again, I want to show you this, but I'm not going to require you to do this for your test. It is in the book, and there are some examples. You will need to know it for 340 lab, but for 210, if you know walking, jogging, and cycling, you'll be fine. So let's look at the cost of walking. So the total O2 needed, or the gross VO2, is your net VO2, meaning what we just discussed, the horizontal component and the vertical component, plus rest. Basically, you figure out the O2 cost of walking on flat land plus walking on the incline or vertical component, and then you always want to add rest. So this is another commonality. You're always going to add 3.5 mils per kg per minute to our total because that is your resting VO2. We're going to calculate the VO2 energy cost associated with walking flat and on an incline, and then we're going to add resting to that. We'll do the same thing for jogging. So an example, when we start plugging in values, we have the units, but for this example, we're going to just use that coefficient of 0.1. S is the speed. This is the horizontal component. This is the vertical component, 1.8 times the speed, and then also this is the grade. So if I want to calculate the O2 cost of going up a hill, I need to know the percent incline, and I also need to know the speed. If I'm walking slow up a relatively flat incline, that's a totally different caloric expenditure than if I'm walking rapidly up a steep incline. So S equals the speed in meters per minute, and G equals the grade. We're going to express that grade as a fraction. And then we also have our resting component. Let's look at an example. So what are the estimated steady state VO2 and METs for walking speed of 3.4 miles per hour? So the first thing that we want to do is we're going to multiply 3.4 miles per hour times 26.8 meters per minute per miles per hour. So this is a conversion factor. I've written it here so that you can see that we're canceling units. The miles per hour. Anytime you have a negative exponent, this -1, it notes a rate, which is miles per hour. So 3.5 miles for every hour. The rate per hour is represented by this negative coefficient. Same thing here for my conversion factor, 26.8. I have meters per minute. That's what, when I combine this, which is multiplication, times the -1, this means per. So it's 26.8 meters per minute per miles per hour. There's a supplemental video on negative exponents that will really clarify this if this is something that you're unfamiliar with or you're already confused. Basically, when I look at this equation, all I have to do is multiply 3.4 times 26.8 equals 91.1 meters per minute. All right, so the first thing that you do is convert miles per hour to meters per minute. How do you do that? You multiply by 26.8. I'm showing you how the units cancel for your benefit. So now let's solve. Once I've converted to meters per minute, I'm going to solve for 3 components: the horizontal, the vertical, and rest. Luckily, I don't have to solve for rest. It's going to be 3.5 every single time. So let's look at this. This person is walking flat. There's no incline given. And sometimes students get confused. Basically, you can do that calculation, but the percent incline is 0. So for that vertical component, anything times 0 equals 0. So the 0 cancels out. So the horizontal portion, I take the 91.1 meters per minute and I plug it into our formula. So 91.1 meters per minute times 0.1 mils per kg per minute per meter per minute. The 0.1 is a given coefficient. It's what I multiply speed by to get the flat portion of walking. Then I'm going to add resting, which is 3.5 mils per kg per minute. 91.1 times 0.1 will give me 9.1 mils per kg per minute plus 3.5, which is resting, mils per kg per minute, equals a VO2 of 12.6 mils per kg per minute. That's the O2, steady state VO2 for this particular walking speed. Now, to get to METs, I simply divide by 3.5, because remember, 1 MET equals 3.5 mils per kg per minute. All right, so let me show you that proof for METs. So I have a VO2 equals 12.6 mils per kg per minute. I have my METs equals VO2. I'm going to divide by 3.5 mils per kg per minute. So METs equals 12.6 mils per kg per minute divided by 3.5 mils per kg per minute. That's going to give me 3.6 METs. So the estimated steady state VO2 for walking at 3.4 miles per hour in METs is 3.6 METs. When you look at the physical activity compendium, you have MET values for a lot of different activities. This is how they do it. So that's the proof. All right, well, let's look at this. What's the VO2 of a female walking at 2.5 miles per hour? Is there a difference in the energy cost for males or females? No. That's why I put that on there, so now you know that fact. So let's look at this proof. First thing I do, remember, is multiply by 26.8 to change my miles per hour into meters per minute. So 2.5 miles per hour times 26.8 meters per minute per miles per hour. How did I get this? It's a given. It's just a conversion factor. I have a video on conversion factors also available in Oaks if this is something that confuses you. So 2.5 miles per hour times 26.8 meters per minute per mile per hour equals 67 meters per minute. Then there's nothing about incline. So this is flat. So I'm going to use my 0.1 mils per kg per minute per meter per minute, which is a given. And I'm going to multiply that by speed in meters per minute. So 67 meters per minute times 0.1 mils per kg per minute per meter per minute. And then what is this part? That's rest. So I'm going to add rest. I'm alive the whole time I'm walking. So this is the I'm alive part. This is the hey, I'm walking part. So you probably do this in your head. 67.0 times 0.1 is going to be 6.7. So 6.7 mils per kg per minute plus 3.5 mils per kg per minute is going to give me 10.2 mils per kg per minute. All right. Well, now if we can calculate METs, let's calculate caloric expenditure. So to do that, I need two additional pieces of information. If I know METs, I'm going to need to know body mass in kilograms. How do we get there if we know body mass in pounds? We simply divide by 2.2. So I need to know the weight or the body mass, and then I need to know the number of minutes that that person is walking. So for this one, if she weighs 59, and this is the same example we just used, if she weighs 59 kilograms and walks for 30 minutes, what's her caloric expenditure? So her VO2 equals 10.2 mils per kg per minute. We just saw for that. So to get METs, we take 10.2 mils per kg per minute and divide that by 3.5 mils per kg per minute per MET. That gives us a MET value of 2.9. So I can already say with 2.9, that's right below moderate. So there's not going to be a very high caloric expenditure. So we take our METs, which we just calculated, 2.9. We plug that into the formula that I provided in part 1. 2.9 METs times 3.5. 3.5 is a constant. It's a given. Times 59 kilograms. I multiply those out, and then I divide it by 200. 200 is a given. It's a constant. That gives me 3.0 kcals per minute. So if she walked at this pace for 30 minutes, she would burn approximately 3.0 times 30 equals 90 calories. So 3.0 kcals per minute times 30 minutes equals 90 calories. Well, what if her husband, who weighs 220, was walking with her? So how many calories would her husband? So we take 220 and divide by 2.2 to get 100 kilograms. So he's walking with her. So he's walking the same speed. So it's 2.9 METs. But now we go 2.9 METs times 3.5 constant times 100 kilograms. That's his body mass. Divide all of that by 200 and we get 5.1 kcals per minute. If he walked at this pace, the same pace as his wife, they're walking together. He's being polite. He's walking beside her, not getting out in front of her. If he walked at this pace for 30 minutes, then he would burn approximately 3.0. That's a mistake. It should be 5.1 times 30, not 3.0. So it's 5.1 times 30 equals 153. This number is correct, and this number is correct. So if he walked at this pace for 30 minutes, then he would burn 5.1 times 30 equals 153 calories. I'm going to stop right there. And for this portion, I'll be back with part 3 and a couple more proofs plus running. And then I'm also going to do one with the incline. So I'll see you in a little bit.